technical difficulty. So I'm Jamal Lewis. I'm with Rewiring America. I am going to talk about residential electrification costs and benefits. I want to acknowledge that I want to acknowledge my colleagues, YL and Amanda, who were really helpful in putting together this presentation. And we're just going to get right into it because I know we're over. Next slide, please. So here's what we did. We modeled operational cost savings when upgrading when performing a residential heat pump upgrade and comparing that to a high efficiency gas furnace upgrade. So an operational cost means what does it actually cost to operate, and that often is represented by utility bills. We also looked at upfront costs. So what does it cost to purchase the piece of equipment and install it? And we modeled that for all homes in the building stock. And we modeled that based on both heating and cooling capacity. And then we looked at the impact of federal and state incentives in reducing upfront costs. Next slide. Here's the data that we use to model. We use RESTOC, both the energy modeling and building stock data, the E3 building decarbonization study to model electricity and gas rates, which will impact the operational costs. And then we took upfront costs derived from Tech Clean, which is a heat pump program in California, as well as Mass Saves, which is a heat pump program in Massachusetts. And we adjusted those costs using RS means, which is a data set that is used by construction professionals across the country. We used fossil fuel equipment costs by RMI and also adjusted those based on RS means. And then we looked at eligibility data for Maryland state incentives provided by the Maryland Energy Administration, Department of Housing and Community Development, and utility incentives. And then we also used the Inflation Reduction Act's consumer rebates that Director Pinsky talked about, as well as some consumer tax credits that are available for heat pumps. Next slide. So here's the summary, the overarching summary of what our analysis came to. We found that 98% of Maryland households would have lower operational costs, so their bills would be lower when using a heat pump when compared to a high efficiency gas furnace. The median low income household would save $373 every year when upgrading to a heat pump compared to a gas furnace. The overall state average is $465 every year. What are the driving factors? Gas costs are expected to increase 3 times over the next 20 years, while electricity costs are only expected to go up 13%. And heat pumps are more efficient in terms of technologies. Households that are eligible and get rebates lead to shorter payback periods. And the 500,000 households not eligible for rebates will have a longer payback period. Next slide. So we're going to look at upfront costs first, and then we're going to look at operational costs and then payback periods. So in total, when comparing the cost of a fossil fuel upgrade to the cost of electrification, the cost of installing a heat pump with a panel, the installing a heat pump with panel upgrade costs about $6,000 more currently. And these upfront costs vary by home size and system capacity. We are comparing the heat pump to a furnace upgrade and a separate air conditioner because we are looking at the overall cost of being able to provide both heating and cooling, which is a standard that we would like everyone in Maryland to have. So if you have a furnace, odds are you're gonna need a separate AC unit, whereas a heat pump can provide both of those services. Next slide. So these next couple slides are meant to be taken from the perspective of a homeowner or a consumer looking to upgrade. So how much would I pay as a consumer to install a heat pump versus a furnace plus AC? This first slide is for low-income households, defined as residents earning 80% or below of area median income. So in Baltimore City, for a one-person household, that's about $62,000. For a three-person household, it's about $80,000. And this households earning below 80% of area median income, there's about 380,000 of these households across Maryland. These households are eligible for both utility incentives as well as rebates from the Maryland Energy Administration. And this program is called the Low and Moderate Income Energy Efficiency Program, where consumers can get up to $12,000 on an upgrade that includes an HVAC upgrade. So as a resident, if I'm looking to install a heat pump, taking into account the utility incentive, the utility heat pump rebate, as well as the rebate from the Maryland Energy Administration, there's still a $2,800 remaining cost that I would need to pay. In comparison, that last bar on the right that says $0 is taking into account the cost of upgrading to a furnace and AC. There is no additional cost. The size of the incentives are large enough to make this a zero. To reduce or eliminate the upfront cost. Next slide. So this next slide is meant to show the cost for low-income households who are eligible for, again, the utility rebate, as well as the Department of Housing and Community Development's whole home efficiency program. And taking both of those incentives gets you down to about $6,600 in extra costs for installing a heat pump. Again, if you're looking to upgrade to a high efficiency furnace and AC, the value of the incentives bring that upfront cost down to zero. Next slide. So there are there are two current incentives and then a pending incentive with the Inflation Reduction Act rebates that are hopefully going to hit the streets later this year. This is the third of the low-income incentives, in which households can get up to $12,000 for both a heat pump and a panel upgrade. And so for low-income households who are eligible, you can see that there's still a remaining cost of about $2,800. And again, if I'm looking to upgrade to a gas furnace and AC, that comparative cost is zero. Next slide. For moderate income households who are also eligible for the Inflation Reduction Act's rebates. So moderate income defined as between 80 and 150% of area median income. There's about 580,000 households within that range. These households have a remaining cost of about $8,500. But compared to the cost of replacing with a high efficiency furnace and AC, it's less. There's still an $11,000 cost for these households for replacing with a. Thank you, Nicola. We'll add that in. There's still a cost for replacing with a high efficiency furnace and AC. And I will note that the cost on the previous slide for low-income households, the upfront cost was about $15,000. The cost on this slide, the upfront cost is $18,000, and that's representative of home size. Middle-income households typically have larger homes, and so the upfront cost is going to be higher because of that. Next slide. And we also looked into multifamily. We looked at the Multifamily Energy Efficiency and Housing Affordability Program. which modestly decreases the cost for multifamily units. This is for multifamily properties that have in-unit heating and cooling systems. So still a pretty significant remaining cost there. Yeah. And then finally, we looked at higher income homes. Again, the upfront cost is higher because higher income homes are larger on average. And there are about 45,000 households qualifying or that are higher income, defined as above 150% of area median income and above. And these households are eligible for and likely to have sufficient tax liability to be able to take advantage of the federal tax incentive, which is a $2,600 tax credit that you can get for installing a heat pump and also a panel upgrade too. So that brings the cost down modestly, but there's still a pretty significant remaining cost and still a pretty significant cost if you're looking to upgrade to a furnace plus AC. So in total, if Maryland were to provide enough funding so that no household across Maryland had any upfront costs, that would be this bottom number, about $31 billion. Yeah, next slide. So that was upfront costs. Now we're going to look at the impact on utility bills, which otherwise known as operational cost savings. Next slide. So this looks at heating fuel by current heating fuel. So across Maryland, there are households heating with electric resistant heating, natural gas, propane, and fuel oil. And so we looked at the average cost, the average annual savings by upgrading to a heat pump compared to upgrading with a high efficiency furnace. And so the red line or the red bar represents the high efficiency gas furnace. The yellow looks at the heat pump. And this graph shows savings, annual savings. And so the savings are higher in every case for those using a heat pump. And the savings are pretty significant. Up to $700 a year for those currently heating with fuel oil. Next slide. And so we just took that same graph and looked to see if there were any differences when you broke it down by income. And those savings numbers, annual savings, persist, remain relatively stable when looking across incomes too. So low-income households save pretty significantly, middle income as well as higher income. And we also looked at it based on building stock type too. So the annual savings every year, or the savings every year, are pretty significant for those heating with heat pumps versus those using a gas furnace. Next slide. So we've looked at upfront costs, and what we found is that there is still pretty significant upfront costs. And then we looked at operational costs. And so what are the savings every year if you choose to go the route of a heat pump? So now we're going to look at if every household did choose in the current incentive environment, if every household did choose to go with a heat pump, how long would it take to recoup that cost? Leveraging the operational savings that you get every year. Next slide. So there are two rows here for low income. There's the top row represents low income households that don't get any or that don't have any upfront costs because the incentives are large enough to cover the upfront costs. So these households get instant savings. So as soon as they put a heat pump in, they're getting a saving. They're getting savings that year. There are some low-income households who, where there is some upfront costs, and that's the net upfront cost column. In which case, there's a payback period between 0 and 4 years. But you can see the vast majority of low-income households, about over 500,000 of low-income households across the state. In the current incentive environment, they're getting instant savings. For moderate income households, again, instant savings, and in fact, you would be paying more to upgrade with a high efficiency gas furnace when compared to upgrading with a heat pump. And so not only are you getting instant savings, but you're also saving based on otherwise investing in a high efficiency gas furnace. There is, for higher income households, as where there's a pretty significant gap. Again, we model based on building size as well. So the upfront cost is inclusive of larger systems needing to heat and cool larger buildings. There's still good annual savings, pretty significant annual savings, but the net upfront cost is pretty high. And so the payback period can vary between 4 and 18 years. Next slide. And the payback periods vary or don't vary when looking at building type. So for single family detached, single family attached, and multifamily, the payback periods are about the same. And there, this chart represents households that are not eligible for rebates or incentives. These are higher income households. So among the higher income households, this is what this chart represents. There's still a pretty significant payback period of about 8 or 9 years on average. Next slide. So here's some additional considerations as you digest this data. Our modeling was done for heat pumps only, not other electric appliances like induction stoves or heat pump water heaters. We did not model the additional impacts of building envelope efficiency measures, but insulation and other weatherization measures are important and will enhance energy and bill savings. There will be an additional cost for those measures, but they will definitely enhance the bill savings. Some homes, will require additional funding for pre-weatherization and pre-electrification measures to address health and safety hazards like lead, mold, and asbestos. So these homes will require additional funding, and we did not take that into consideration here. Next slide. So here's the final slide. The key takeaways. The upfront costs of switching to an electric heat pump are higher when compared to upgrading to a high efficiency gas furnace and AC. For those who qualify, incentives for heat pumps are attractive and lead to short payback periods, but there is limited funding, which means only a small proportion of households can be reached. Upgrading to an efficient electric heat pump would be more attractive to households across Maryland if incentives for gas upgrades were limited. It would take about $31 billion to cover the upfront cost for every Maryland household upgrading to an efficient electric heat pump. And again, 98% of households will have lower energy costs by upgrading to a heat pump when compared to a high efficiency gas furnace over the span of 20 years. These savings are largely backloaded because gas prices are projected to increase steadily through 2040. So that is the those are our key takeaways, and would be happy to answer any questions.
All right. Jamal, can you hear me okay here? About 10 minutes for questions, and then move on. We have a new mic.
Someone moderating the questions.
Can anyone hear us here? It doesn't look like they can hear us.
Yeah, we can hear you.
We can hear you. Director Pinsky, I see your hand up.
Yeah, I've got 2 questions, Jamal. Early on, when you talked about low income, the first number was like 350,000. Then the DHCD number was like 530,000. which is a more accurate number, if I can use that term. I don't know if accurate is the right word. And are those overlapping numbers, or are they different subsets? Do you know that?
I'm sorry. I think you're referring to the number of low income households. Is that what you're referring to?
Yes.
Yeah, the eligibility criteria are different for MEA's programs when
Right.
compared to the Department of Housing and Community Development. I think both are fairly accurate, but they're slightly different thresholds, which means it's going to result in a different number for the definition of low income household.
Okay, and the second question, and this is maybe when we get to talk policy.
Yep.
If there's a $31 billion liability to get everybody on the heat pump, two things. If we made it income eligible, and people over over a couple $100,000 were not added, and if we, for example, reduce the savings to low income from $400 to $250 a year, and use that money to underwrite the initial cost of what was the $31 billion liability. I mean, is that a possibility? And is there some modeling that could be done to figure out some cost-effective ways to still reduce the pressure on low-income families and have them make money or save money, as well as have the upfront costs utilized, but maybe also include some of that money in paying off the major upfront cost, as well as maybe taking out the people over $250,000 with tens of thousands of square foot homes?
Yeah, if I understand your question, you are it sounds like you're asking, how do we reduce the upfront cost for low-income households, recognizing that there is significant utility bill savings when switching to a heat pump? So can we tap in?
You froze on us.
Can you hear me?
Now we can. Yeah.
Yeah. The computer I was on just died, so using my phone. Can we tap into the utility bill savings to help cover some of the upfront costs? That was the question?
Yeah, and also maybe not cover a heat pump for all income sectors. I guess I'm jumping to solutions, and that'll happen in a subsequent meeting, but I want to see what some of the options on the table are.
Yeah, I think that there are ways to do that. There's a concept called on-bill financing, where you take where you do dip into the bill savings and you use that to cover the upfront costs. You basically I guess the equivalent of a loan, but then that loan is paid back using a percentage of the bill savings that you get every year. That is a concept that's used in some jurisdictions across the country. That is a possibility to be incorporated here, particularly given the scale of savings that the majority of Maryland households would get.
Great, thank you.
Of course. I see Senator Kramer.
Yeah, thanks, Jamal. Question, did you all look at life expectancy of the two options, the package HVAC furnace as opposed to heat pump? I know that I had asked the question of my HVAC contractor, who indicated that typically heat pumps are rated with a life expectancy of somewhere to 25 to 30% less than that. So they are replaced with greater frequency, although he said his real world experience is that they do seem to fail before that, that they're even shorter life expectancies. But I also had read an article that there's an increased failure rate for heat pumps in what are referred to as coastal areas, and that their life expectancy is reduced even more. And certainly Maryland, as we all know, has significant coastline, so I don't know what qualifies as a coastal area. But did you all maybe, or are you going to take a look at that aspect of, if we do make the conversion, the frequency with which the residents will then have to be replacing these units?
In the analysis that I just presented on, we assumed about 20-year useful life for both machines. But that is something that we can look into further.
Yeah, I mean, even looking online, I think the best case scenario for heat pumps at the outside is 15, with, from what I've read, 10 to 15 is probably the span. So I just think it would be, something that should be looked at. What is the frequency with which people will have to then be replacing this equipment? Because I guess we also need to know, will they be able to be continuing to get rebates going forward if they have to be replacing these units with greater frequency? Just a thought.
I really appreciate that, and we'll definitely look into that, and we can get back to you.
I see Kathy Magruder's hand up next. So, Kathy, can you confirm if you hear me saying that?
I can hear you. It's a little choppy, but I can hear you.
Well, please go ahead then.
Thank you. Hi, Jamal. I'm Kathy Magruder with the Maryland Clean Energy Center. And my question for you with regard to your comments about on-bill financing, in those states where that is a model solution to address this, can you talk about where the lending capital comes from for the loans? Is that utility capital, and at what rates?
I would need to get back to you on the rates, but it is utility capital. It is an emerging market or emerging solution that is largely unregulated at this point too. So I think if this is a direction that Maryland would go in, I do think we need to spend some time thinking about best practices around that.
I see Mark Case has his hand up, and I think that.
Wait, I don't know if that was sufficient, Kathy.
Thank you. Yes.
It's a question for this section of the time, so we have time for the follow-up offline and in future meetings. But let's go ahead.
Marcia, did you?
I said, Mark, please go ahead with your question.
Okay, thanks. This is Mark Case, BGE. Yeah, it may have been outside of the scope, but I was curious if your modeling, did it look at sort of system impacts? Did it look at the amount of peak load growth that would occur on the electric system under the adoption of the heat pumps that you've modeled, and what sort of costs occur on the distribution, transmission, and generation side? And then second question, was hybrid heating an option that you considered at all, or do you have any thoughts about that?
We did not consider hybrid heating, and we also did not consider impact on the grid. I guess broadly, as we are increasing the electrical demand, it is important that the electrical infrastructure is upgraded to meet that demand. But I think it's important to note that demand increase isn't all going to happen overnight. And so we do need to make the proper investments in that infrastructure over time to meet the gradual growth in the electrical demand. Does that make sense?
Yep, that's helpful. Thank you.
Yeah, of course. Are there any other questions?
Yeah, I'm Nathan Freidinger. I'm with the Hagerstown Light Department. I might have missed the beginning of the presentation. I noticed there was $650 utility rebates applied towards these incentives. What is the origin of those funds?
The utility rebates,
Correct.
those are part of the Empower program.
Okay.
So those are
I don't know if you're aware, the 5 municipal electric companies in the state, Hagerstown, Vermont, Williamsport, Berlin, and Easton, they're not in the Empower program. So we
That's
don't
right.
have it available.
That's right. These are the investor-owned utilities across the state.
So for our customers, would they still be eligible in some way?
For municipal utilities, if there is not a municipal incentive, I believe the answer to that is no.
Okay.
Yeah.
Thank you.
Of course. Were there any other questions?
In the interest of time, we're going to have to probably call it there for Jamal's presentation. I see some more questions in the chat, so we can make sure those are followed up with in the chat, perhaps, and hand it over to Josh from PNNL, if that's all right with folks. I hate being the bearer of bad news, but someone's gotta police the time. Did I say PNNL? Josh with the LBNL. Apologies.
Yep, no worries. Can everyone hear me all right? We can hear you.
Yeah, you're good.
Okay, great. So yeah, a little bit garbled still on our end, but we'll make do with what we have. So yeah, appreciate you all taking the time to let us talk through some of this analysis that we've been performing with the MBE team. Just for a little bit of context here, Lawrence Berkeley National Lab, in addition to Pacific Northwest National Lab, are both here. We have Kevin Madison here from the PNNL team, who's involved with the cost analysis. I'll be doing the presentation here, but in terms of questions, we have Kevin here as well to help support. And in addition to that, we have Travis Walter from our team here at Lawrence Berkeley National Lab that did a lot of the initial impact modeling, stock analysis modeling, and then the subsequent cost benefit analysis. So all very excited to be here. To contextualize it a little bit, we are part of a broader network here. So in partnership with our friends over at the National Renewable Energy Lab, NREL, sponsored by DOE and EPA to support building performance standards and their implementation. So the work that we're going to be presenting today is work that we're working on with jurisdictions across the country, but always with a regional approach and leveraging regional data as part of our analytics and modeling. So you can hop to the next slide. I'll walk quickly through the agenda here. And also just to quickly introduce myself, many of you have probably heard my voice either in recorded webinar or live during some of our previous conversations, but Joshua Case, I'm a technology researcher at LBNL. Relatively new to the lab. I've actually spent most of my career as a mechanical engineer within the real estate industry. So doing energy auditing, retrocommissioning type work, in addition to energy management planning, strategic decarbonization planning for commercial real estate and associated parties. So was excited to be involved with this initiative when I joined the lab, and excited to present some of these findings. In terms of what we're going to run through today, I'll start by giving some context on our previous impact analysis that we've delivered for MDE, since that is the foundation of our eventual cost benefit analysis. I'll then be walking through PNNL's retrofit cost meta study that they've been working on for quite a while now across the country, and then bringing those things together, some of the analysis results from our full cost benefit analysis. So this will be very much in line with Jamal's presentation, just a different building sector, obviously, that we're looking at here. And I will also note that we're not considering incentives in any of the analysis that we're showing up until now. So obviously, that's something that would be a component of the conversation when it comes to overarching financials. And then we'll conclude with all of our wonderful results that we have. Next slide. So just to give a basis here, there were two components of the analysis that we had to perform in order to deliver our initial impact analysis. That started with a building stock analysis. So this is a process of understanding what is the baseline energy consumption of each asset and the associated carbon intensity. Across the state of Maryland, we had a good amount of benchmarking data, not from a state mandate, but from EPA's portfolio manager, which is a combination of regional benchmarking data in addition to those that are voluntarily reporting either for their own purposes or for other reporting programs. So we leveraged all of that data in order to develop a baseline scenario. And then the impact analysis was essentially a iterative effort of modeling different policy scenarios to understand the impact on a macro basis. So are we hitting the goals that we expect to hit if we implement certain targets in certain years across certain metrics? And we did a bunch of that model as part of the impact analysis. Next slide. In terms of a little bit of the nuts and bolts of that analysis, as you can see here, this is sort of an input and output. We're taking in a list of buildings. We're taking in energy and emission data across those buildings, in addition to whatever we have in terms of asset characteristics. And then we're turning that into a stock model and scenarios for BPS targets. We do this analysis by building, by year. So there's 3 different compliance periods associated with the Maryland BEPS ordinance. And so we're essentially modeling out the behavior of each individual building, where they stand today, each of the interim targets that they need to hit. What are they going to do to hit their respective targets towards the future stock scenario? Next slide. In terms of the specific data used for the Maryland analysis, we started with the draft Maryland covered buildings list, which was at the time originally around 8,500 buildings. I think we're up to now 9,300 buildings in revisions of the covered buildings list. We took site UI information in addition to electric to site ratios, meaning the percentage of energy use in a building that is electricity. From this broader EPA ESPM data set, it was a aggregated data set, so fully anonymized data across the assets, but able to leverage property type and size information from those buildings to understand the distribution of energy intensity values. It's important to use a distribution here and not just work off average estimates, because otherwise every building would be hitting the target around the same point if it was estimated data, which is not the reality of how buildings operate or how the policy will end up impacting individual buildings. So we use distribution ratios to understand where higher performer, lower performer buildings, higher UI buildings, lower UI buildings modeled across the entire state. Another important aspect of the analysis is the electrification side. So making sure that we have an understanding of the end use information, specifically with the direct emissions side of energy use within buildings, so that we could start to break down electrification scenarios in terms of space heating, electrification, water heating, and other. We also took in projected grid emission factors provided by MD. The impact model itself, in terms of the basic logic that it follows, so each building will go through steps of this process as they're evaluating their own performance relative to the targets. They first start by hitting their direct emissions target with efficiency, if possible. We did limit this stage of the process to a limited amount of efficiency gains, simply because you don't want to be overhauling a gas system if you're eventually looking to electrify that system. So, but we did want to make sure we were modeling out those that were close to the target, that they would have the opportunity to commission their system, put in operational measures that allow them to eke out a bit more efficiency from those systems. And then from there, the behavior would be to electrify systems if efficiency can't meet those targets, and looking individually at space heating, water heating, and then other uses we looked at as its own bucket until you hit your direct emissions target. And so again, the theme here being you start with the most cost-effective measures and then you invest in more capital measures as needed to hit the increasingly aggressive targets over the course of the compliance periods. And then once those measures are taken across the gas use, which, as we all know, when you electrify a system, you're going to be using more electricity after that. The building will then reduce however much they need to in order to hit the site UI target that's been set for the individual asset. So this analysis, again, every building, every year between now and 2040, how do the buildings behave to comply with the target set? Next slide. This is the macro output of our impact analysis. And so this is across the entire list of covered buildings that we were looking at. Line charts here essentially showing a business as usual scenario in red, a direct emission only scenario in blue, and a direct emission target plus site EUI target in green. The left-hand chart is showing it on an energy basis, whereas the right-hand chart is showing it on an emissions basis. I think the main takeaway here from an emission standpoint is that the greening of the grid is something that is considered as part of the business as usual scenario here. So your red line, your business as usual line, is still reducing emissions tremendously, purely based off of the greening of the electricity consumption and the decarbonization of the grid from that standpoint. And so this essentially shows the emissions over time, and then we output both the emissions at the final target period, in addition to cumulative emissions over that time period. So you can see that just looking at the area between the curves of the blue line and the green line, you'll see the additional cumulative savings that you get out of site EUI targets in addition to the direct emissions target. Next slide. All right, from here, I'm going to hop a little bit into the PNNL analysis. So this is, thank you for shifting the slide there. This is a study that PNNL has been working on for quite a while now. It is a national meta study that's being performed, but performed nationally with the specific intention of delivering regional cost factors. So the understanding is very clear that the building stock within a region, the climate zone within a region are going to be huge determinants of the overall costs associated with BPS retrofits. And so the analysis itself is wide-reaching in terms of the data sources and the literature that were brought in to establish these cost estimates, but special attention was also paid to Maryland-specific literature and resources. So we have a specific call out here for Stephen Winter's Building Energy Performance Standard Technical Analysis that was delivered for Montgomery County, which was a great source of information there, of engineering group that dove a lot deeper into potential prototype buildings and ECM packages and scenarios. Once all the measures are gathered, they're translated into a common framework. And then when needed, when information can't be sourced directly within the region, RS means location factors are used to normalize costs between the region that the data is coming from and the region that it's going to, in this case, the state of Maryland. The Maryland specific analysis also, as noted here, includes 3 components. The energy efficiency retrofit costs, which I'll get into the curves that were developed as part of this piece of the analysis. I noted before electrification, we bucketed into 3 different intervention points: space heating systems, domestic hot water, and then other. And then the third piece that we modeled out was normal same fuel replacement costs for those fossil fuel fired systems. The general idea here being that if you are electrifying any of your systems, that is a brand new system that you have in place afterwards. You would, under normal circumstances, need to replace your gas system with another gas system. And so we wanted to make sure those costs were accounted for in the overall analysis. Next slide. I'm imagining that the text is probably a little bit small on the screen, particularly with some of these slides here. So I will talk through some of the relevant detail here, and certainly the slides will be then available afterwards. But here we're talking through essentially the effort that was taken to tailor the specific analysis to Maryland, selecting the right measures, making sure that they're regionally adjusted. And then, one of the big components of this analysis was, because we're looking at such a wide tranche of buildings, how do we generalize these ECM packages in such a way that we could apply them to certain prototype indicative building types across the stock in such a way that is acceptable and allows for a wide range of different savings that are needed at different facilities. And so PNNL used the specific ECM data, which I'll show in a couple lists in subsequent slides, essentially to build out curves. Those curves representing a interval amount of energy that needs to be saved and the cost associated with that amount of energy savings. The idea of that curve is that it's less aggressive initially because there's more low-hanging fruit opportunity available, and becomes more and more costly over time as you look to get deeper and deeper energy savings at the individual asset. Also, just of note here, multifamily, office, and warehouse were taken as the 3 main prototypes as part of this analysis. Again, the goal of this analysis was not to be hyper detailed to every individual property type and every system type and configuration, because that would be an extremely difficult process without the data to support it. The goal is to get broad statewide costs estimated as part of the analysis. Next slide. I imagine if there was any trouble reading the previous slide, there's going to be a lot of trouble reading these slides, but I can talk through things a little bit here. These are just examples to show the process that went into developing these cost curves. So each row within this hard to read table is a energy conservation measure that's been identified as relevant to that particular prototype building, and then sorted by the overall cost effectiveness of that measure. So essentially the measures that have the lowest cost per kBTU of savings are prioritized as the initial investments that are made, all the way through to then lower savings ECMs that have higher costs by ratio. So towards the end of this list, you'll get into things that cost a lot more, save less relative to those costs, but that's part of the process here, right? It's not just about low-hanging fruit anymore, it's about deeper, more intensive energy savings at buildings. You could hop to the next slide, and we could show a similar chart for office buildings. Same general idea here, right? So we are walking through individual measures and opportunities, and associating those with a certain amount of energy savings at the asset and ever increasing amounts of cost relative to those measures. You can hop to the next slide. So all of those rows that we were showing in the previous table, those are the dots on these charts here. So the x-axis is representing the amount of EUI savings in kBTU per square foot. So as you move to the right, you're saving more and more energy at the building. And as you go up the y-axis, those are the costs associated with those measures on a per square foot basis. And so as you can see, a curve like this, it's relatively cheap to implement low-hanging fruit ECM measures. And then over time, as you look to deliver deeper and deeper energy savings at the asset, costs are increasing more and more rapidly over time. And you can see that the curve fits are pretty strong here. And we were then able to take these curves and implement them within our impact model to deliver the analysis that I'll get to. Next slide. Probably in the interest of time, I'll try to move a little bit quicker through some of these slides. That was what I showed before, was specifically on the efficiency side. For electrification retrofits, the sources were a little bit more specific to studies as listed here. So there was a cost-benefit impact analysis done of the DC BEPS ordinance. We also took into account the Stephen Winter study that was done that I had mentioned previously, and then E3's building decarbonization study, where we also sourced the future rate information. Also had good information around electrification and associated costs that went into these values. They were delivered because of the limited amount of information we have on the individual buildings on a per square foot basis. So again, high level estimates here, normalized to the square footage of different assets in terms of estimating the cost there. Next slide. And then beyond that, we looked to model out the base case gas systems. As noted before, this was important for us to make sure that we understood the full value of electrifying a system and the fact that you are most likely replacing an aging system within the building. And so both ASHRAE 90.1 standards, in addition to some translation that had to occur to get this into normalized costs on, again, a per square foot basis, was developed by PNNL for implementation here. So we can go to the next slide. It has some detail on how this was calculated for a specific asset type. So this is, again, just a individual example of a building, but a large office simulation prototype, which is part of the 90.1 minimally compliant scenario. The associated boiler costs. In an ideal world, we'd be doing this on a kBTUH basis for boiler capacity. That's how these systems work, but we don't know the size of the boilers in every individual building across the state, as much as I would love to know that information. And so from that standpoint, this is where the square foot estimates needed to come into play. And this is just demonstrating essentially how that calculation is done using the prototype building as the normalization factor. Next slide. All right, and so with that, we have all of these wonderful sets of cost information and cost frameworks that were built out by PNNL. We have this impact model that our team built out here at LBL. We brought those things together to deliver this cost benefit analysis. Next slide. For the rate projections, as I mentioned before, we utilized the E3 study for building decarbonization. I believe that Rewiring America and Jamal's team utilized similar rate information on the residential side here in order to model out the potential savings. And so you can see how those rates, both electric and gas, are trending over time. Next slide. Once we have all of this information together, we essentially perform this analysis across the different buckets. So the interventions bucketed into electric efficiency, gas efficiency, and electrification. And then from an ongoing cost perspective, looking at what are the business as usual electric costs, gas costs, and then what are the intervention scenario, electric costs and gas costs. And in the most recent iterations of this analysis, we're also starting to bring in the alternative compliance payments as part of it. But I will say that for the purposes of the financials that we're showing here, we're assuming that these particular buildings are not paying any alternative compliance penalties. They are buildings that have behaved in such a way that they are implementing measures and achieving the target reductions. Next slide. So this is us essentially taking your the entire building stock and drilling down into one specific building that I'm not getting into specifics about the building because of just the broader nature of this analysis. We would never hand these financials to an individual building and tell them that this is going to be accurate for that building's situation. The idea here is that the information is accurate on aggregate across the building stock, but it is still helpful to look at individual buildings to see how they perform. We wanted to take a building here that was on the smaller side. So this is, I think, around 47,000 square feet. And it also had an early investment in electrification. So this was important for us to see and understand because when you're looking at rate projections moving forward, as gas rates go up, electrification projects get more and more financially viable. By finding a building that needed to electrify early in the process, we're able to observe what would be a more difficult financial situation here. So in this chart, we're showing the blue bars are representing the 3 intervention points and the associated investments that were made at those intervention points. Again, combination of electrification and efficiency. As you can see, this first bar here was an investment that then yielded a certain amount of electric and gas savings, represented by the orange and gray bars. As the project was looking to pay back, you could see that with the yellow line is the overall financial balance. Once that yellow line crosses the x-axis, the 0 point, the project has hit its payback period. But before it was able to hit its payback period, it needed to do more investments within the building, namely the electrification of the space heating systems. You can see afterwards the gas savings are significantly higher. The electric savings actually go into the negative. When you're looking at this building on a longer outlook, this is just through 2040, you could see here it was important for us to model through 2050 because some of these interventions are happening pretty late in the process. And so once the interventions are fully in place in that final period between 2037 and 2040, there are savings that are being realized post 2040 that are really important to bring into the overarching analysis here. So this is just one indicative building to look at. You can hop to the next slide. And here are the statewide results in terms of our numbers calculated. So this is representing just a hair under 1 billion square feet across the state. The baseline energy costs associated with that is on the order of $69 billion. So this is combined money spent between 2025 and 2050 in the business as usual scenario. And then you could see some of the investment costs on aggregate as well. So business as usual replacement cost came out to be around 0.9 billion. That's a good number to compare to the electrification investments of $6.4 billion. Just to show you how much higher we are estimating that the electrified equipment is going to cost relative to the business as usual system replacements. And then we also are showing the efficiency investments numbered at $8.8 billion here as well. So total energy cost savings. So if you were to aggregate and compare to that business as usual case, all of the gas and electric savings across all of the buildings across this period through 2050, that would pencil out at around $22 billion for a net overall savings of 4.5 billion. These are the overarching numbers. Again, I'll note that the energy efficiency and electrification incentives are not being included within this analysis. And there are also some caveats that I'll get to in a couple of final slides around how to look at these numbers. But hopefully this gives a broad idea of where things stand. You hop to the next slide. These are some of those numbers shown on a per square foot basis. So you could see here how some of these numbers pencil out in terminology that I know the real estate industry may be able to wrap their heads around a little bit better on per square foot cost estimates here. You'll notice the numbers are all relatively similar, and that's because we happen to have close to 1 billion square feet total. So those numbers on a per square foot basis are pretty comparable to the absolute numbers, just moving the decimal point for the most part. And then from there, we could hop into the couple of the caveat slides. Some contact information for those that are looking to reach out. From P&L, some of these cost caveats. So as I mentioned before, costs are high level. They should not be used to estimate the cost of retrofit at an individual building. The list of energy efficiency measures is not exhaustive. It's the best available list that was able to be developed. We're also not looking at any future technology advances as part of this effort. Capacity-based costs for those gas systems are based off of the best estimates that we have on a square foot basis, as noted through these final couple bullets, and then you can hop to the next slide. From LB&L's standpoint on the impact analysis, these are rough and best available estimates. We use any information that is available to us, but there is a lot of gaps in terms of specifics within buildings. I know from having worked in many buildings that every building is unique and does require a different approach. We're really looking to show aggregate numbers and effects here. This also is an important one. ECM Metrolife was not taken into account for this analysis, so we are not assuming, I believe someone may have asked a question around this, costs assume no net changes in maintenance or upkeep of systems. So to Senator Kramer's point earlier, when you are looking at heat pump systems relative to standard systems, there is a difference in overall lifetime there that I think should be taken into account in the future. I think the one mitigating point relative to that is that heat pump systems are also reversible, and therefore they're providing both heating and cooling in most cases, and therefore running the entire year as opposed to just running during one season. For the purposes of our analysis, just because we don't have information on what's happening within systems, those cooling systems and heating systems are handled entirely separately. So, when you put a heat pump in, you're replacing potentially two systems with one, and those two systems would need to be replaced as opposed to the one system that would need to be replaced potentially on a higher frequency as a heat pump. So I'll make that note here. And then yes, like for like systems were assumed to be replaced in accordance with the electrification retrofits for the business as usual scenario. We're not adjusting for inflation. We're not taking into account future efficiency electrification technologies that aren't currently commercially available. So I think that's about it for me. Appreciate everyone's time here, and I will do my best to try to call on folks. I'm not sure who raised their hand first, but
yeah, for folks who are in the room, we are continuing to experience some issues here, so we'll just do online conversation. I saw Kathy's hand, and then Paul, and then Tom. But yeah, Josh, go ahead and continue calling people. It might be easier.
Hey, Josh, I was going to ask you if you could go back to the slide with regard to the investment needed. I just want to make sure that I have the data points clear. I'm hearing you say that to address almost 1,000 million square feet of building area, that we're looking at a approximately $15 billion investment that would result in $22.3 billion in total energy cost savings. Is that correct?
yes, broadly speaking, I think those numbers are correct. Yep.
Okay. And when you say baseline energy costs, help me understand how that fits into this context. I know it may be obvious to others, but that
Sure,
is
no, it's
just
good.
what those buildings are currently paying for electricity.
Right. It's essentially you're taking the existing consumption of that building, assuming it continues business as usual, so same amount of relative consumption year after year through to 2050, what they would spend on aggregate over this 25-year time period.
And do you have a number when you say the net cost savings of all investments? Is that also the net savings in energy costs, or is it the net of the investment minus the baseline? Okay, I see what you have. All right, never mind. Thank you. I understand now.
Great. Yeah, no, it's all good questions, and important for us to make sure that this is clear to everyone. So appreciate your feedback there.
Thank you.
Who's next between the two of you? Is it Paul?
Yeah, I think so, Joshua. And I understand you've done a macro analysis here. And I'm looking at slide 20 of 26, example building. And a lot of the work you've done is 2025 to 2050. I'm just trying to wrap my head around the concept that in the Climate Solutions Now Act, buildings over 35,000 square feet are supposed to reduce or required to reduce their greenhouse gases by 20% by 2030. So it's a bit more near term. So I'm trying to understand your macro analysis of the long term and how that fits with the more immediate 6.5 years of reducing the 20% in, I don't know how many buildings you came up with, or over 35,000 square feet.
Yep. Very good question. I don't know if we could maybe hop back a slide to that point. Essentially, when we did the overarching analysis here, the first compliance period is that 2025 to 2030 range. And so targets that were set for 2030 are being taken into account, and it's usually in this early investment that the goal would be to hit that 20% through that first intervention period. The investment at this particular asset happened in 2025, but the way that the model works, it could happen at any point between 2025 and 2030, depending on when the individual building has the capacity to make those upgrades. But that was one of the interim targets that was set towards the eventual absolute target in 2040 of net zero emissions, direct emissions.
So you're just assuming they meet them. You're not doing the micro analysis of how they meet it or if they meet it. You're assuming they will meet it in terms of your broader overarching analysis.
Yeah, so the interim targets themselves were crafted in such a way that you would hit that 20% value in that first compliance period. So that was something that was fed into the targets themselves. And then this analysis here is essentially just showing how a building gets there, how a building gets to that first interim target. Does that make sense?
Yeah, I'm not sure I saw where they get to the 2030 target or how they get to the 2030 target. Maybe I missed it because it was, as you said, a pretty overarching approach. So.
Sure. Yeah, and I think we do have more information on the impact model overall. We didn't want to dive too deep into early stages in this conversation, but we could definitely send that along.
Thank you.
Sure.
Thank you.
All right, Tom.
Hi, Joshua, Tom Ballantyne with NIOP. I think I know the answer to this, but there is no cost of capital borrowing cost in here. In your
correct. Yes. Yeah. No cost of capital.
And my other question is along the lines that Secretary Pinsky was asking. It's on the total annual emission reduction if we implement what you've modeled. Can you put a number on that, or does the model provide it?
The total annual say one more time for me, Tom?
Emission reduction results from implementing these practices.
I see. Yeah. I don't know it off the top of my head, but we definitely do have those values for you. So we could make sure that those are submitted and within the documentation here.
I saw that you provided your email at the one of the final slides. It's okay to follow up with questions.
Yep, absolutely.
Appreciate that.
Yeah. Thanks, Tom. Michael?
Yeah, hi. Thank you. I work on doing retrofits on buildings all the time from the design side. So I noticed that in your ECM table, though, you're right, the text was small, it was hard to see. So I'll be interested to look at the slide deck later. Did I only see one envelope measure being R5 insulation? Just because the envelope being more durable than, say, the heat pump, there is then, I guess, a time value of the durability of that investment. And I know that would be adding a whole other layer to your analysis. But in terms of if you can use low global warming potential materials to achieve more durable, deeper energy reductions, I wonder if that, would be something we could consider in a future study, or if that, what else you might have been thinking about during that ECM list derivation.
Yep. Thanks, Michael. That's a good question. And I am just pulling it up on my screen to reference that list in terms of envelope upgrades. We do have as you note, the R5 wall insulation. Also R10 roof insulation is one of the later measures. And I know windows as well, improved fenestration, and envelope leakage reduction is one of the earlier measures in there. But to your point, we're not modeling out all of those potential interactive effects that I think could be valuable for future bits of analysis or evolutions of the analysis.
And did you say envelope leakage, meaning air infiltration?
Correct. Yes.
Okay.
Sure.
So this also related, I noticed, when dealing with multifamily affordable housing, there are regular cycles of refinancing. And at that time, many things are changed out anyway. And I think you talked about that with respect to the gas furnace, for example. But there are many times when we've worked on projects and we're like, okay, this is our bite at the apple. We're going to replace all the things that are at the end of their useful life. And those things happen on a 15-year cycle, as I understand it, for a lot of affordable housing. In any case, I thought it would be interesting to see how the cost of those, let's say R5 insulation, we typically add R10, R20 insulation to walls, R20 or 30 to roofs. And those costs, if you're going to be doing the roof anyway, or you're going to be recladding the building anyway, or you're going to be replacing windows anyway, those become incremental costs rather than total cost figures. So I was wondering how you were assessing those costs, just out of curiosity.
Yeah, no, it's a good follow-on question there. And I don't off the top of my head know how much the individual measures within there were incremental as opposed to absolute costs. You're absolutely right that, as much as you can be opportunistic about your upgrades, right? Work is already happening at this building. Let's make sure we do that work in the most efficient way possible. It's definitely a big part of the process. But I'll have to get back to you in terms of the specific measures there.
And my last question, and I'll make it very brief. In the first set of slides you showed were really compelling to have a flat line in terms of energy use, and yet a decarbonization line for the red line related to business as usual because of the decarbonization of the grid. My understanding is that the levelized, normalized cost of, say, insulation is radically lower than the cost of the decarbonization of the grid, which is to say building whole new solar developments plus storage or whole new transmission lines. So if we were to do a statewide smart analysis about this, we'd actually have to look beyond our state and think in terms of the levelized cost of the grid improvements, which are like $2 or $3 trillion over the next, 10 years, versus the value of putting on some insulation on a low income family home. to bring down the grid demand in the first place. So it made those two graphs made it look like, oh, you know, we really shouldn't bother with the building too much because the grid is getting much better. But that was just a carbon emissions. It wasn't carbon emissions per cost, and it wasn't a carbon emissions per cost as related to other comparative measures like a very inexpensive insulation or air sealing package. So I thought those charts were really awesome and compelling, but also potentially very misleading, because it made it look like maybe we shouldn't be doing this. And the final piece of that is it also did not include the cost of energy that would be saved. So if you were to track the net outcome of energy savings against the cost of the improvements, you know, the cost of the improvements combined with energy look different from just looking at the energy saved. So there's a sweet spot where the knee bend happens and it starts getting more expensive. I think it was a cost curve you had where the costs were going up for more aggressive measures. That was maybe the next slide or the following. So those two charts were really interesting to me. And I think that if we had follow-on analysis, we'd want to layer another layer of nuance onto them so we don't get misled by them, if that is fair. I mean, it's excellent analysis. It's just not the whole picture, right?
No, absolutely. I definitely agree with your points there. And it was actually a consideration of ours in showing this chart because the red line does look pretty good, right?
Yeah.
The business as usual scenario there. And we are also doing, I'll quickly note some peak demand analysis on a more broad basis to help understand, you know, what point for our covered buildings are we going to hit winter peaking as opposed to summer peaking, and how much are the site UI targets and the efficiency measures potentially going to mitigate those changes in peak demand. To your point of, hey, if you could tighten up an individual building, that's going to be what is the term, megawatt, is much better than having to build new generation from it. So,
like the house behind me is zero energy, and it used to be a hog. And so we don't put any stress on the grid today, but everyone else is putting stress on the grid. And that has another whole layer of cost for the utility because peak energy demands are so much greater. So that's yet another level of analysis.
Sure. Yeah.
Unfair to put you on the spot for all that, but it's important in the long run.
Yeah. You know, appreciate that feedback. And I will hand it off to Kevin here from the PNNL team. I see you have your hand raised there, Kevin.
Yeah, thanks, Josh. I just wanted to address quickly Mr. Hindle's comment about marginal cost and in the EEM list. So that was a meta study that some of my colleagues did that looked at secondary sources. So there's no original research we didn't actually go price out these things. We looked at other people's work. And indeed, some of those studies are looking at marginal costs that to incorporate those measures into work that was already going to happen. So I just wanted to affirm that. And Josh, we can figure out which of those measures are marginal costs and which are incorporated into work that was already happening and sort of true interventions that were motivated out of saving energy only. And we can get that information together.
That's great. Thanks, Kevin. Appreciate the additional insight there. Looks like Kevin's still talking and not hearing him. Anyone else have that issue?
Nope.
Okay. I just assumed that was a glitch in the matrix there. But apologies, Kevin, if I'm the only one who couldn't hear you. Nicholas, I believe your hand's up.
Yeah, thanks. So I'm looking at slides 10, 11, and maybe I'm just being a little thick, but I don't see a column that measures the savings per cost per square foot, sort of, and I think the way I've usually seen it in energy audits is either stated as a payback period or the inverse. And I think that would be very helpful for building owners to see it measured that way, potentially even prioritized that way, so that they can understand the efficiency of their investment and they can prioritize what investments they're making as they contemplate how they're going to reach compliance, and also by building type. So maybe I'm missing it, but that would be helpful data to include if it's not in there.
Yeah, no, thanks, Nicholas. Appreciate that. And yeah, I guess because they're not necessarily looking at energy rates within the establishment of those ECMs, that the columns in the table are a little bit more abstract than the typical payback periods. But I do believe it's something that could be added there. I'll talk with Kevin and the PNNL team about that, just because I agree it would be a helpful reference point to see those payback periods across each.
Even if it's reflected differently, again, something that shows folks the cost efficiency of ECMs.
Right, sure. Thanks for that. Any other questions?
I think we have to return to the agenda. We're a little over time. Serena or Mark, you want to try to recoup the last few items we have?
Can you hear us at all?
Mark, you're a little bit choppy.
Yeah. I had luck holding it like a microphone. Sorry, we're still having issues with the microphone in the room. So we're going to conclude today's meeting and pick up with the remaining agenda items at next month's task force meeting.
At the last meeting, we received the impression that subgroup would be meeting over the summer with a draft report in September. That's 2 months. That's not a lot of time. I recommend that we start on that before next meeting.
Yeah. Actually, Cindy, since it looks like you're in a place where you have better audio, would you be able to say briefly what the status of the subgroups is? I know you put that in the chat earlier, but a member in the room wasn't able to see that.
Hi, yes, I can give a quick update on the subgroups. So the 4 subgroups are listed on the website. I had put it in the chat. I'll put it in again. We've gotten a lot of interest, about over 20 participants per subgroup. We've gotten interest in subgroup chairs as well. We are planning on reaching out in the coming weeks to schedule the first meeting per subgroup. It'll be in August. And then we're planning on having 2 meetings in September per subgroup. If you've reached out to me, you're in the list. And I'll put my email as well. You can still sign up, so just let us know if you're interested, and if you have any questions, I'm happy to answer them as well by email.
Thanks, Cindy. And to all online, we really apologize for the audio issues for today's meeting. We will again try to correct this for the following meeting, which will take place in about a month from now. We'll send out some information by email about content from today's meeting and get ahead to the next meeting. Director Pinsky, because people can hear you better than they can hear us, would you like to make any concluding remarks?
No, it's a lot of great information. If my head wasn't spinning before the presentations, it really is spinning now. Just trying to grasp all the information. Very important material to use as a foundation for our future work. So I want to thank the presenters as well as the participants for being engaged. And hopefully this can lead to a lot more strategy and solutions over the next few months. Thank you.
I'd like to add just, thank you, Director. I'd like to add just a couple of few closing remarks. Can you all hear me okay?
We
Still,
can hear you. A little choppy, but we can hear you.
oh, so annoying. I'll try to be clear. I think the topics that we talked about today is so important, you know, as we go forward and look at the full picture of recommendations and what we really need to do in order to come up with some good recommendations. So when we looked at home electrification costs, the cost benefit analysis that was presented by Jamal, who did a really great job. Thank you for that. That's a good consideration for us, as well as BEPS cost benefit analysis. That's the second piece of it that I think, you know, just seeing and hearing about those two areas and learning about the analysis and the cost benefit of home electrification and all of that is so important. We did miss the third one, right? The third presentation, which was co-benefits of building decarbonization. I think that's a nice segue into the full picture of what we need to be looking at. I will ask, are there any other, thank you, good to see you again. Are there any other pieces of this puzzle